Okay, the definite integral. All right, so in 5.1, we learned that we can approximate the area under the curve using the Riemann sum. All right, so in the talk of Riemann sum, we're looking at something like that. All right, and now remember that the area that we approximated, it becomes much better if we have many strips. So if we try to have as many strips as possible. All right, so the more the strips, the better the approximation of the area. And now this brings us to this question. So how many strips do we actually need exactly, or to get an exact answer? Because we want to get some specific answer for area, but how many strips are we going to need to get some exact answer? And the answer is infinitely many, right? So how do we actually do this? The idea is to use limit. So if I use infinite number of strips, infinite number of strips, I can do this by saying the limit as n tends infinity. Right? Remember, n stands for the number of strips. Right? So if we say the limit as n tends to infinity of the sum from I equals to 1 to n of fxi delta x, this gives you some exact answer, right? Or some exact area. All right, and then we call this the definite integral of f. All right. And that brings us to the definition of a definite integral. So to say if f is a function defined for x between some closed interval a, b, we can divide the interval a, b into n sub-items with equal width. Last time I showed you guys how to compute the width. The width delta x is just b minus a over n. All right. Now, if you let x0 all the way to xn to be your endpoints of this subintervals, and you let x1 star all the way to xn star to be sample points in this subintervals, um, we want those sample points such that xi star lies in the ith interval, right, of this closed interval here, xi minus 1 and xi. Then we define the definite integral of f from a to b. We define that as the limit as n tends to infinity of the sum from I equals to 1 to n f xi star delta x. All right. We say provided that this limit exists and it gives the same value for all possible choices of a sample point. And we say that if it does exist, we say that f is integrable on that closed interval. Now, notice this symbol here that I've introduced is the integral sign, all right? And we say it's an elongated S, right? And we choose that because we say the integral is just a limit of sums, okay? Now, let's say in the notation, remember this notation that you've seen there, integral a to b f of x dx. F of x there is called the integrand. So integrand is just the function you're about to integrate, all right? And then a and b, we call them the limits of integration. I'm sure you guys have had, we call it the bounds, all right? Lower limit, upper limit, or you say a is a lower bound and b is the upper bound, all right? So for now, we're just gonna assume that this dx, they has no meaning, all right? In a nutshell, we can say that dx is just represent the independent variable. For example, if I say integral of f of x dx, it means I'm integrating with respect to x. If I say dx, it means with respect to x. All right. And that whole procedure of calculating integral is what we call integration. All right. So let's see. So say for definite integral from a to b f of x dx, we said this definite integral can be interpreted as the area. So always think of integral as the area under a curve. Y equals to f of x from a to b. All right, so we're looking at the area of this region here. And you must take note that if your area looks like this, you see that the region on top of the x-axis will give you some positive area. The regions here at the bottom will give you negative area, and then this one obviously will give you positive area. the total area now is going to be these two regions there at the top minus the one there at the bottom. All right. This is just what I was explaining. So take note that you're going to get positive area, negative area, positive area. All right. Let's look at the properties of the definite integral. The first one, very important, it says that if b is bigger than a, all right? Remember, your integral is normally from some number a to b, where a is smaller than b. So if we say that b is bigger than a, then if you have the integral from b to a of f of x dx, you can swap it around and you introduce a negative sign. So integral from b to a can be written as minus integral from a to b. For example, if I give you the integral from 2 to 0, I expect you to quickly observe that this doesn't look very cool because you're supposed to start from a smaller bound to a bigger bound. So you need to swap them around and then you introduce a negative sign. So you're going to say minus integral from 0 to 2. Right. So you have to keep that in mind always. And then if you integrate from a to a, so if the bounds are exactly the same, the integral will just be equal to 0. For example, integral from maybe 2 to 2 of some function x, it's just going to give you 0. All right, the integral from a to b of some constant, remember if you take the antiderivative of a constant c, you get c times x. And if you substitute upper bound minus lower bound, you just get c into b minus a. All right. The integral of the sum of two functions, you can see, is just the sum of the individual integrals. All right. And then the integral of a constant times a function, you can always take the constant in front of your function. All right. And the integral of the difference of two functions is just the difference of the integrals of both functions. So make sure you remember those rules. Let's look at example 6. So use the properties of integrals to evaluate this one here. So integral from 0 to 1 of 4 plus 3x squared. Let's do it step by step. First thing you can see is the sum of two functions. So I can split the integral into two. So I have integral from 0 to 1 of 4 plus the integral from 0 to 1 of 3x squared. Now for the first one, the integral of a constant 4 just becomes 4 into upper bound minus lower bound. All right. And then obviously we need to find this integral here. And the integral of x squared on its own from 0 to 1, remember if you find the antiderivative of x squared, you get x cubed over 3. And if you plug in upper bound minus lower bound, you just get 1 over 3. And therefore, this integral simply becomes 4 plus 3. Remember that we wanted 3 times x squared. So you say 3 times this result here. So 3 times 1 over 3. And that just gives you 5. All right. Now, very important, the next property tells how to combine integrals of the same function over, very important, is adjacent intervals. All right. So if you try to integrate from a all the way to b, you can write this as the integral from a to c plus the integral from c to b. That is just equivalent to the integral from a all the way to b. All right. So that adjacent interval, you can see you have AC and CB. All right. So you have two intervals that you're looking at there. And we can apply that idea here to do example 7. If I tell you that the integral from 0 to 10 of f of x dx is 17, I give you the integral from 0 to 8 of f of x dx, I say it's equals to 12. Then I say, what is the integral then from 8 to 10 of f of x dx? Now you can already see I give you 0 to 10 and integral from 0 to 8. So you can start by saying that the integral from 0 to 10 is equivalent to 0 to 8 plus 8 all the way to 10. Now this is what you're looking for, this piece here. So you just need to make that the subject. So you take this piece here to the other side. And if you do that, you have the integral from 8 to 10 is just the integral from 0 to 10 minus the integral from 0 to 8. So just 17 minus 12 is 5. Very easy, right? All right, so let's look at more properties of definite integer. All right. So the properties we saw before 1 to 5, they're true whether a is less than b, or a is equals to b, or a is bigger than b. Now, for these properties, we're going to stick to the fact that a needs to be strictly less than or equals to b. All right. So we call this the comparison properties of integers. So say if f of x is greater than or equals to 0, what this statement simply means is if f of x is a positive function, all right, and x lies between some closed interval a and b, therefore your integral, your area is also going to be positive. Remember, this integral is just area. So the area of a positive function between some positive interval will definitely be positive. All right, that's just what 6 is saying. Now, if f of x is bigger than or equal to g of x, so what this statement means is f of x lies above g of x, and x lies between a and b, then the area of f of x must also be bigger than the area of g of x. All right. And then for 8, we say if f of x lies between some two numbers, so you have m and capital M, so it is smaller than capital M, but is greater than or equal to small m, and x lies between this closed interval a, b, then look at what happens. So if I apply integral all through, um, you see that the integral of the curve will also lie between m into b minus a, small m into b minus a. And you know where this is coming from, because if you take the antiderivative of a constant, you just get the constant times your variable of integration, which is just x. And if you apply your upper bound minus lower bound, then it just becomes that constant times b minus a. All right. We can see that graphically. I'm going to show you guys quickly what property 8 is saying. The area under the curve, so if you notice it, this curve here lies in between capital M and small m. Notice that the area, if you look at this area here below small m, you see that it is definitely smaller than the area under the curve. All right, it's smaller than the area under the curve. And similarly, the area under the curve is smaller than the area of this region M. Remember, M is this whole rectangle there. You can see that. So hence we get that relationship, that the area of your curve needs to be smaller than the area under M, which is that whole box there, and it has to be bigger than the area under small m, which is this small rectangle here at the bottom. All right. And guys, that is basically it for this first piece of definite integral. If there's no question, I'm going to move to 5.3.